So we're just going to talk right now for a few minutes about what it means to be a confidence interval and the things that make up a confidence interval. So we have here the Pew Research Center, and they surveyed 1,200 adults between the ages of 55 and 74, and they're saying that the proportion of people who use social media regularly in that age group is between 0.167 and 0.213. So I just want to talk about this confidence interval thing for a minute. When you take a sample from a population, so they've sampled 1,200 adults in this age group. Clearly there's way more than 1,200 people in this age group in the United States, but they've taken a sample. And we now want to make an inference about the population. So they get a proportion from their sample, and then some calculations happen, we'll talk about that in a few minutes, and they come up with this interval. So they don't say exactly 27% of US adults between these ages use social media. They say, we are 95% confident that the proportion who use social media is between about 16.7% and 21.3%. So it's like a range.
Is it kind of like R?
Not quite, no. This is truly this is an estimate of the proportion of US adults in this age group who use social media. So they're saying we are 95% confident that between 16.7% and 21.3% of adults in this age group use social media. They can't give an exact number, right? We can't possibly go out and ask every US adult in this age range if they use social media or not. So we take a sample, and then based on the sample, we do some calculations. That's coming. And we get this confidence interval. All right, so let's talk about what it means to be a confidence interval. A confidence interval is constructed by starting with what's called a point estimate. Now, a point estimate is either going to be a mean or a proportion. So this is either going to be x bar or p hat, depending on the type of data we're looking at, right? Means versus proportions. And then we add and subtract what is called the margin of error. It's a phrase you've probably heard before, margin of error. So what I'd like to do first is just look at this confidence interval here, this 0.167 to 0.213, and I'd like to kind of work in reverse to get the point estimate. So I would like to find the point estimate for the given confidence interval. So in this case, this is a proportion, so my point estimate is going to be p hat. The point estimate is dead center in the confidence interval. So the question we're asking is, what number is dead center in that confidence interval? Well, I can say to myself, I can find how big this range is. So I'm going to go 0.213 minus 0.167. And that will give me 0.046. So that's the distance between the 0.167 and the 0.213. So it ranges sort of like 4.6 percentage points. Now if I want to find the point estimate, I'm going to divide this by 2 for 0.023. And 0.023 is now the margin of error. It's the number that was added and subtracted to the point estimate. So to get p hat, my point estimate, I'm going to take my 0.167, which is the lower end of my confidence interval, and I'm going to add 0.023 to it. And I get 0.19, and this is my point estimate. Again, the point estimate is just the center of the confidence interval. So I found the difference between the smaller and the larger number in the confidence interval, divided it by 2, and that's the margin of error, and I added that to the 0.167 to get my point estimate. So here's what I want to show you. Here's generally how you would write. So I'm going to start with my point estimate. Plus or minus, we found the margin of error to be 0.023. It's very nice to see your confidence interval broken up with the point estimate and the margin of error. So if I take 0.9 and subtract 0.023, I'll get that 0.167. If I take 0.19 and add 0.023, I will get that 0.213. So when I went out and did this survey of 1,200 people, 19% of them said, yes, I use social media. 19%. That's the number I got from my sample. Then some calculations happened because we know just because these 1,200 people, 19% of them said, yeah, I use social media, that does not mean that exactly 19% of all people in this age range use social media, right? It's an estimate, it's a point estimate. And then we do some calculations to get the margin of error, and we say, hey, we are 95% confident that the true proportion of people who use social media is between 0.167 and 0.213. All right, we're gonna get to those calculations in a minute. Right now we're just kind of talking in general about being a confidence interval. Okay, so after you construct a confidence interval, you're typically asked to interpret it. So this is sort of a fill-in-the-blank type of situation. This is wording works perfectly every time, all right? So I'm gonna interpret this confidence interval with 95% confidence. Now, your confidence level isn't always 95%. You could go with 90%, you could go with 99%.
Does it give it to you?
Yeah, so when you're asked to construct a confidence interval, it'll tell you what level of confidence that you want. You gotta think, the more confident you'd like to be, so if I wanna be 99% confident, I'm probably gonna get a wider interval. So there's a little bit of a balance between like how confident do you wanna be, but how much spread do you wanna see in your confidence interval? Because I could say to you guys, I am 99.9% sure that the temperature tomorrow is going to be between -15 degrees and 90 degrees. Because that's a huge range. I can be really, really confident in that, but it's meaningless. So sometimes you play a game where you're like, how confident do I want to be, but I want an interval that's meaningful. Okay, so I'm going to interpret this confidence interval. We are, so this is a fill in the blank, whatever level confident. We are 95% confident that the interval from 0.167 to 0.213 captures the true, and then in context you write what the thing is. Okay, so we're 95% confident that the interval captures the true proportion, because this is a proportion, of U.S. adults aged 55 to 74 who use social media to update about themselves. So you're always going to say that you are, and then your level of confidence, name the interval, and captures the true either proportion or mean. In this case, we're talking about proportion, and then context. This is how we're going to write our interpretation every time. Now, here's a very subtle difference. There's a difference between interpreting the interval and interpreting the level of confidence. Okay, so here I'm interpreting the interval. What does it mean, the 0.167 to 0.213? What does it mean? It means I'm a certain degree of confidence that I've captured the true proportion. But I want to talk about the confidence level. So to interpret a confidence level, this is really about like confidence in your methodology. So if we take many samples of a size, in this case 1,200, from the population, about 95% of them will result in an interval that captures the true proportion. So this is another sort of fill in the blank kind of thing. So if we take many samples of size, and then you name your size, in this case 1,200, from the population, about whatever percent your confidence level was, 95% of them, will result in an interval that captures the true proportion of what you're looking for. So what that means is, using this method with this specific sample size, 95% of the time I'm going to get a number that's accurate. So what does that mean? It means as this is a confidence interval of 95%, means we don't have 100% faith in our answer. So like if we look at this interval again, what this is saying is, if I were to do this over and over again, get different samples of 1,200 and build a confidence interval, 5% of the time, the true proportion of people who use social media in this age group is not in this interval. So 5% of the time my interval is incorrect. 95% of the time I capture the true proportion, or in some cases mean, of what I'm looking for. Okay, so how do you calculate a confidence interval? Well, you get a statistic, and again, that's going to be x bar or p hat, so we're going to focus on proportions in a minute here. And you add or subtract to that what's called the critical value, more to come on that, times the standard deviation of the statistic. So that's a little vague. However, we're going to start to kind of fill in the blanks a little bit. So I just want to point out on the blue sheet, under inferential statistics, which is where we're entering, here's where it says your confidence interval, you take your statistic and you add and subtract the critical value, we'll talk about what that is in a minute, times the standard deviation of the statistic. Here are these little formulas that we were using back in chapter 7. Those are still going to be the formulas we're using moving into chapter 8. Okay, so if you're working with a mean, it's the standard deviation divided by the square root of n. If you're working with proportion, it's this little guy here. The critical value we'll get to in a moment. The critical value is related to the level of confidence, right? Because you have to build the level of confidence into the interval somewhere. Okay, flip your paper over. And we're going to start talking about proportions. So there are conditions that have to be met in order to construct a confidence interval using a population proportion. You have to have some sort of randomness. You have to either have a random sample or random assignment in an experiment. Randomness is critical. If you're looking at a sample, you have to check the 10% condition. If you're working in an experiment that has random assignment, you do not need to check the 10% condition. But if it's a random sample, you do.
How do you do that again?
So that is that you have to show that the sample is not more than 10% of the population. We'll do an example in a couple minutes.
So you have to say like there's more than
Correct.
1,200.
Yeah.
involved.
Yeah. And the second condition is the large counts condition. And that's that n times p hat, in this case, and n times 1 minus p hat are both greater than or equal to 10. Okay, so we have to check these two conditions before we can move forward in our confidence interval. All right? Conditions. And then, what we're going to be talking about is a 1 proportion z interval, specifically called a 1 proportion z interval because in the next chapter, we're going to have 2 proportion z intervals. Okay, so this is a 1 proportion z interval. Here's what it looks like. You start with your p hat. So you go and you do your thing. You ask your question. Do you use social media? Do you have a dog? Whatever it is. And you get p hat, right? That's your sample proportion. And you add and subtract to that the critical value. Well, here in proportions, the critical value is called z star. I'll talk more about that in a minute. And then that gets multiplied by the standard deviation, which is p hat times 1 minus p hat over n, the whole thing square rooted. So, I mean, p hat's p hat, right? It's like the proportion you get from your sample. N is always the sample size, so that's fine. Let's talk about what this z star is. So, if I said I wanted to calculate a 90% confidence interval, and I would say, okay, well, 90% confidence interval is going to be centered in the normal distribution, 90% confidence interval. So I've got some things on the ends that aren't included. So if this is a 90% confidence interval, that means there's 10% remaining, which means there has to be 0.05 on each end for this to be a symmetrical distribution. So remember, if you're using the table always gives you the proportion to the left of the value that you were talking about. So right here is the number that I need. And this corresponds to a proportion of 0.95. So I want to get the z that corresponds to 0.95.
Well, what about the other 0.5?
So we only have to take care of one end because the distribution is symmetric. It's going to work itself out. Once we get into a couple of examples, all of this will make much more sense. So we're going to go to our table, and we're going to find as close to 0.95 as we can. And it's somewhere in here. Let's see. Oh, I'm looking pretty good right here at 1.6. So I'm kind of in between right here, so I'm going to go 1.645. So my critical z value for 90% confidence would be 1.645. Now, I'll remind you that you guys have graphing calculators, and so we can use the graphing calculator for this too. If you don't have a calculator, grab one, because I want to make sure that we're clear on that. All right, so let's talk about where we can get this critical z value from the calculator. So under distribution, there it is, inverse norm. Now again, like when we're using the table, we only have the option of left. So we had to convert the 90% confidence interval to an area of 0.95. Remember, if you're working in the normal distribution, your mean is 0 and your standard deviation is 1, so I'm going to leave this at left for now. And there's the 1.645 that we determined from the table. Now, the calculator is smarter than the table. So we could, let's just double check and see, put in the true area of 0.90 that we want, but center it.
Nice, Anna.
And hopefully, we get the same thing. So now it's giving us both the lower and the upper end, but all we care about is the upper end for this particular. Your z star should always be positive. Always positive.
Can I go?
Yeah. Okay. We're going to do more of that in a minute. But I want to just outline one last thing, and then we're going to do some actual problems. Okay? We are now moving into the 4-step process. Your book has talked about this for a while, and I've said we don't need it yet. We don't need it yet. But for here on out, for confidence intervals and inference testing, we are going to talk about the 4-step process. The 4 steps are state, plan, do, and conclude.
Do we remember those?
All right. State. You're literally going to write the word state. And it's going to feel a little bit repetitive because you're going to kind of like restate what the problem is telling you, but it's actually really good practice. And it's going to make sure that you're clear on what it is you're doing. So you're going to state, you're going to name the parameter. Mean or proportion, depending on the situation. And the confidence level. and you're going to use context. That's step one. So we're going to say something like, we are going to find the true proportion of US adults between the ages of 55 and 74 who use social media with 95% confidence. It's going to feel a little bit redundant because it's sort of like built into the problem, but it's going to help you really clarify what you're trying to do. For your plan, you're going to name the method that you're going to use, and you're going to talk about conditions for that method. In the do, you're actually going to perform calculations, and then in conclude, you're going to conclude. So you're going to like interpret, in this case, you're going to interpret your confidence interval in context. Okay, we need to see what this looks like. As usual, seeing an example helps to clarify what's happening. So, got a few examples ready for us. Maybe an extra there. Okay, let's see if we can put this all together. That's a lot of words. Let's do some actual calculations. Here goes. I'm going to try to reach 1 minute to see if my, put yourself back in here. Sorry.
Wait, can you slide it back so I can make the last one?
What's that?
I think it should.
Oh, yeah, sorry.
Thank you.
Let's go. There it is. All right, let's put this all together and actually construct and interpret a confidence interval. First one's not very exciting, it's about beads. That's okay. All right. We have a jar that has 3,000 beads in it, red and white. We do not know how many of each. That's what we're going to try to write a confidence interval for. So we take an SRS. And in the SRS, we get 107 red and 144 white. So to be clear, here's our goal. Our goal is to find the true proportion of red beads. I want to know, is there 40% red beads? Is there 27% red beads? What proportion of this jar contains red beads? Now, I'm going to get a sample proportion, and I'm going to use that to build a confidence interval for the whole jar. Right? So here goes. We're going to state, plan, do, conclude. State. We want to calculate.
No.
Hello.
Change that forward real quick.
Okay. We want to construct. I'm going to say construct a, let's see, 90% confidence interval for the true proportion of red beads in the jar. So, like I said, a little bit redundant, but it's clarifying exactly what we're going to do. We're going to construct a 90% confidence interval for the true proportion of red beads in the jar. I could dump them all out and count them, but I don't want to do that. I want to take a sample, and then I'm going to construct a confidence interval based on the sample. Here is my plan. If conditions are met,
Thank you.
we will use a 1 sample Z interval for proportions. I'm going to check my conditions now, but I'm going to say it. I'm going to say I have to check the conditions, and if they're met, I'm going to use, in this case, a 1 sample Z interval for proportions. Next class, we're going to talk about a 1 sample T interval for means. So we have to be really clear on what it is we're doing. All right, well, let's see. This is an SRS. So that's good, that gets the random piece in there, right? SRS is a simple random sample. And I need to check the 10% condition. So let's see, it looks like my sample was 107 plus 144, so my sample size was 251. So I have to check that my sample size is not more than 10% of my population. And I should be good because the population is 3,000 beads, and 10 times 251 is 2,510, which is less than 10,000. So I'm going to write that down. This is an SRS. And there are more than 10 times 251, or 2,510 beads in the jar.
What if there isn't?
Then we'd have to stop and say, okay, and let me tell you, in a free response question, that will never happen.
Yeah.
It could happen in a multiple choice, or a question where they're like, explain why you can't do this thing, and then you'd like be like, hey, the 10% condition hasn't been met. So if I had taken a sample that was 400, my calculations moving forward just wouldn't be something I could rely on. Okay? But in a free response question, you should expect things to check. It's more like in a multiple choice or in a find what's wrong with this problem kind of situation.
Yeah.
I also have to check the large counts condition. So I'm going to check n times p hat. Well, I guess I got to figure out what p hat is, huh? P hat is the proportion of red, and 107 out of the 251 of them were red, which is 0.426. So p hat is 0.426. So I'm going to check the large counts condition. Here it goes. Large counts. N, which is 251, times p hat. We'll check that. And n times 1 minus p hat. We'll check that. Are both at least 10. So let's see. 251 times 0.426 is about 107, and 6.9, and then 251 times 1 minus 0.426 is 144. So we're definitely safe in the large counts condition. Okay, I have stated my plan, and I have checked the conditions, and I'm ready to do. Okay, so I'm going to put up here, here's how we're going to construct our interval. We're going to take p hat, and then this is where we get our margin of error. Margin of error comes from z star times the standard deviation of the statistic. So I have my p hat. I'm going to have to find my z star in a minute here, and then I'll plug my stuff into my standard deviation formula. All right, p hat is 0.426 plus or minus. I got to find my critical z value, so I'm going to go to my calculator. And I am constructing a 90% confidence interval, so I'll leave that at 0.90. And remember we said we can keep it at 0.90 if we keep that in center. So z star is 1.645 times the square root of p hat times 1 minus p hat over n. So let's see here. I'm going to get my margin of error. 1.645 times the square root of 0.426 times 1 minus 0.426 divided by 251. Make sure it all looks good. 0.0513.
So that's the
So I'm going to write it down.
confidence
Yeah, so hold on, 0.05, I'll just go 0.051 since I have 3 decimals for the others. Okay, so I typed this into the calculator, which resulted in the 0.051. That is my margin of error. Margin of error is 0.051. Right, so I've got my point estimate, 0.426, plus or minus the margin of error, and then I'll actually do it so I can get my interval, 0.426 minus 0.051. So on the lower end, I'm at 0.375. And then 0.426 plus 0.051, and my upper end's 0.477. Okay, so for the do portion, I showed my calculation for the margin of error, and I now have a confidence interval. So I'm saying here that the true proportion of red beads in the jar is somewhere between 37.5% and 47.7%. It's kind of a wide interval, but that's what we got with our 90% construction. Now, let's talk about doing this on the calculator, just completely on the calculator. And remember, as I've said all year, it's important to know like what the formulas look like and what the portions of the formula are and where things are coming from. But we do like to rely on the calculator. It makes things faster and less room for like little calculation error. All right, so on your calculator, press Stat and go over to Tests.
Wait, why?
Stat,
Z-test.
Tests.
Where's stat?
Stat. It's 2 over from the green button,
Stat, test.
and then go over to Tests. Now, we're going to be going to this part of the calculator a lot in the next few chapters. And there's a bunch of stuff on here. You have to make sure you're using the right thing, right? So what's nice is these updated calculators prompt you. So if you get into something where you're like, I don't know what to put there, you're probably chosen the wrong thing, right? Remember specifically that we are doing a 1 sample Z interval. So we need to find the thing that says 1 sample Z interval, or 1 proportion Z interval. And there it is, it's down there at A. 1 proportion Z interval. Specifically 1, and Z an interval, not test. We haven't talked about tests yet. So let's see. It wants to know X, N, and our confidence level. So N is always N. N is like the size of the sample. X is how many out of the sample were the thing you were looking for. Okay, so in this case, I got 107 red beads out of a total sample size of 251. I want my confidence level to be 0.90. And then we're going to cross our fingers that the confidence interval the calculator gives us is pretty darn close to the one that we calculated.
So wait, what is
And there it is. Okay, so X is the number of successes, so in this case the number of red beads. N is the sample size, in this case 251. And we did a confidence level of 90%.
Number of successes.
And look at that.
And is number of sample size.
So let's talk about write-up if we were using the calculator on the do part. So this is old school write-up, right? And then if I'm using the calculator, it would look something like this. On the TI-84, a 1 proportion Z interval. And then we're going to tell it, like just like we did in the past, we're going to name the prompts. So in this case, it was X was 107, N was 251, and my confidence level was 0.90. And it gave us the same interval that we got previously. That's always good news. Yay. Okay, that's the do part. There it is. I'm on conclude. So for the conclude, we're going to use this interpreting a confidence interval. So we're going to say we are 90% confident that the interval from blah, blah, blah captures the true proportion of red beads in the jar. here goes. We are, in this case, we did 90%. Confident that the interval from 0.375 to 0.477 There it is. So again, the big idea here is that we take a sample, and we know that the sample is not 100% accurate, right? My proportion of red beads in my sample was 0.426. But that doesn't mean that exactly 42.6% of the beads in the jar are red. I know that that's an estimate, that's my point estimate. Based on the sample size and the level of confidence, I build a margin of error around that. And that helps me construct an interval that I have some level of confidence about. So somewhere between, I'm 90% confident that somewhere between 37.5 and 47.7% of the beads in the jar are red. Kind of a wide interval, that's what we got with our sample size and our confidence level. Questions so far? All right, so I'm gonna have you guys try one. So flip your paper.